11, almost halfway through.
Yeah.
I think so, right?
Yeah.
Our plan for today is just do some more counting. We stopped in the middle of one section, so we're going to finish that up, go work through the next section, and then we'll see how we're doing on time. If we have time, maybe we'll talk about permutations and combinations today. A reminder that if you're going to submit a rewrite for assignment 3, that's due today. And then we're working on a take-home test due on Wednesday. I got some questions via email, and then I thought maybe folks would appreciate seeing those questions or at least my responses, so I posted an announcement talking about those. Are there questions folks want to ask right now?
I'm curious, you said at the beginning you dropped 2 homeworks?
Whatever the syllabus says. I'm not sure.
I just was wondering.
I only have the spring 19. I'll check the syllabus. It's whatever the syllabus says. Yeah. Questions about like the test or assignment 3 if you're working on those rewrites?
I have a few questions about the test.
Mm-hmm.
Question 3. I didn't really make use of the definition of the set in the solution.
Number 3. Okay, so I'm just going to pull it up here.
So I must have done it improperly because I showed symmetry and transitivity without invoking the set definition.
Oh, you don't. I mean, you mean so that's one where you define a relation by saying A is related to B if f of A is equal to f of B.
That's the one, yeah.
Yeah. So the set A, like what specifically that set is, you don't need it to show reflexive, symmetric, and transitive. If we were interested, I don't think the problem asks you to do this, but if we were interested in like figuring out what the equivalence classes were, then that would be important. But you really all you need to do to show that that the relation has those properties is just use the fact that it is a function. The fact that the function specifically is x squared plus 1 isn't even that important. You can use it. People have written it by making specific reference to that actual function. You can actually just do it by saying it's a function. Like if you just sort of go look at the definition of a function and, like for example, is it reflexive? Is every element related to itself? So you could set that up by saying, well, a squared plus 1 has to be equal to a squared plus 1, right? But you could also just say, look, f of a equals f of a. It's a function, right? What makes something a function is that when you plug something in, it can only give one output. So f of a has to be the same thing, right? Like f of a is equal to itself. So and then the symmetric and transitive are kind of using similar arguments there.
I also had a question for reflexive. You have to say that it's true for all elements A within the set.
Within the set, yep.
Yeah, that's not a thing that you have to do for symmetry and transitivity, is it?
Well, yeah. I mean, for reflexivity or reflexiveness, we say for every element A in the set A is related to itself. For symmetry, it's whenever A is related to B, then B is related to A. And I guess the underlying assumption is as long as A, for A and B in the set, if A is related to B, then B is related to A. I guess that's just a tacit assumption.
Okay.
But you don't have to make reference to the specific set. I mean, certainly with reflexiveness, you could say that we're true that f of a is equal to f of a for all real numbers. So certainly it's got to be true for that subset of the reals that we're talking about in that problem. Other questions?
One last dumb question I know there are no dumb questions, etc. For question 5.
Uh-huh.
I don't have the question in front of me, but that was the one where you have to prove B can only for 3 divides n and divides n squared.
Yep.
For 3 divides n squared, implying 3 divides n, I guess I got caught in a loop because it just seems obvious that if 3 divides n squared, then it must divide a factor of n squared. And since the factors of n squared are just n, then it has to divide n. Is that stupid? And
It's not stupid, but I also don't think it's obvious. A lot of the time, you know, when, like, the things that we think seem like, well, yeah, that's got to be true, maybe that makes it harder to write an argument for it. But I don't think we can articulate a reason for it. And when we did in class, we did a proof that if we use the words even and odd in the example we did in class, but I'm going to rewrite it using this notation. We showed that if 2 divides n squared, then 2 divides n. Only the way we worded it was that if n squared is even, then n is even, right? That's how we worded it. But the way we proved that is we used the contrapositive. Because when you start out by saying if, you know, suppose 2 divides n squared, that just gives you like 2 times some constant is equal to n squared. And then you have to get to n. To get to n from that, you have to take a square root. And then there's no guarantee that we're even talking about integers anymore when we have to start imposing square roots. So the advantage to using the contrapositive there was that we got to prove if 2 does not divide n, right? If n is odd, then 2 does not divide n squared, then n squared is odd. Right, and we suppose this, and that got us to be able to say, well, n takes on the form 2k plus 1. And then we could square it and show that n squared had to be odd. You're going to do, I would recommend doing something similar for this direction, that if 3 divides n squared, then 3 divides n. I would show the contrapositive, because that gets you a statement about n that you can then just square, right, to deduce something about n squared. What you need to do, and this is one of the things I talked about in that announcement, was, you know, if something's even or odd, right, like if something's not even, it has to be the form 2k plus 1, right? We know it. There's only one thing to worry about, because the integers alternate, right, every other, even odd, even odd. But the multiples of 3 are every 3, right? So if something's not a multiple of 3, it's either 1 more than a multiple of 3 or 2 more than a multiple of 3. So if you show the contrapositive, this, once you assume that 3 does not divide n, you got to break that into 2 cases. So in case 1, either n is, you know, 3k plus 1, like 1 more than a multiple of 3, or 2 more than a multiple of 3. But so you just work with each of those separately. Regardless of what it is, the result that you get, you could say definitely is not a multiple of 3. You'll be able to write it in one of those 2 forms. Does that help?
yes, it does. Although it does still seem obvious the way I wrote it. I don't know, I'm just kind of confused by it.
Yeah, I
It
mean,
seems like it's a very simple, well, n squared has 2 factors that are the same, and so since 3 divides the composite of those 2, then it must divide one of the elements, which is n.
yeah, you know, it's not, I don't think that's obvious. I mean, n, first of all, n times n is, you know, those aren't necessarily prime factorizations. And is that true for any integer? Like, is it true for, like, if 12 divides n squared, then does 12 divide n? You know, I mean, I think there's some assumptions, and it might seem obvious, but it should be to the point where we can prove it, where we can prove it convincingly, without making any unnecessary assumptions.
Okay.
Other questions?
Could you talk about 7 for a second? Because on 7, I got to a point and I just kind of lost.
Oh yeah, a multiplication table for Z7. So what I'll do first, I think, is I will talk about...
I think 7's not the Z table. 7's it's the 3, 13n minus 6n.
Oh, yeah. Okay, yes. Great. Okay, so that, yeah, that's the induction one. 13 to the n minus 6 to the n is divisible by 7 for all n greater than or equal to 1. So how do induction proofs work?
Well, you start by proving
base case.
that is true for 1.
And that's pretty obvious, right? So you're going to let n equal 1, and then 7 obviously is divisible by 7. So the hard part is the induction step. And how do we start that?
You let n equal k.
Okay. Well, we let n equal k. We're going to suppose it's true for some n equal to k, right? Yeah. So let's suppose. And that gets us, if that gets us 13 to the k minus 6 to the k is divisible by 7. So if it's divisible by 7, it's a multiple of 7.
Yeah.
So it's 7. No, I can't use k. So 7 m, I guess. We get this for free. And I'm leaving out some words, right? We'd say like for some integer m and so forth. Where do we want to go from here? So what's my next expression? Can you turn on your mic?
Would it be 13 to the k times k plus 1?
Well, so what we want to do is just, we want to say, what does this up here, the 13, what does that look like when n is k plus 1? So that's just going to be my exponent. So 13 to the k plus 1 minus 6 to the k plus 1. Right, so you want to show that this is divisible by 7. And obviously that's the hard part. So there's a couple things I'll point out. One is, when we're adding in the exponents, you might find it helpful to use properties of exponents. What does addition in the exponents mean? Like, how could we rewrite that? Yeah, right, so like this, we could rewrite how? Is your mic on? Yeah, it is, okay.
13k times 13 to the power of 1.
Yeah, great. So you might find it helpful to do that for one or both of the terms. And then keep in mind, we're going to use our induction hypothesis, right? This thing that we get for free, we better use it. So maybe try to make a substitution. Like you can, if that's an equation we get for free, then we can rearrange that equation to make some substitution as we see fit. Okay? So it's not the only way to do it, but I think it's the most straightforward way. It's the way most people choose to go. Other questions? Okay. If there aren't any other questions on the test, then we'll kind of pick up where we left off, doing some counting. Oh yeah, okay, so, all right, so we've been working on, I guess, using the multiplication counting principle for the most part. Yeah, that's been what we've been focusing on. So let's do another one. So a bit string, just a string of symbols, like a string of like every character is either 0 or a 1, right? That's a bit string, and we want to know how many bit strings are there of length 5. And then length k, but we'll start out with length 5. So I've got like 5 spots to fill in, right? Each one of these is either a 0 or a 1. How many choices do I have for each of these? Say that again? 2 choices. And once if I picked a 1, right, for the first thing, that doesn't mean I can't use 1 over again, right? So I have those 2 choices always. So 2 to the 5th. What about how many bit strings of length k? Like if I don't decide right out at the outset how many.
2 to the k?
Yep. One of the things that, and actually I think it's highlighted best in the last example, the one that we did at the end of class last week, is when you're using the multiplication principle, are you choosing, in combinatorics we say, are we choosing with replacement or without replacement? And with replacement means once I pick that value, I can pick it again the next time. Like here, I have the same number of choices each time I pick something. If I'm going to scroll up to the last example just so we could talk about that for a minute. We talked about functions mapping elements of S to elements of T. If we didn't, if it was any old function, right, I didn't need it to be one-to-one, then I had the same number of choices, right? Every element, I could map every element of S to the same element of T if I want, right? That's still a function. So in this case, we were choosing with replacement, right? Because I could reuse the same element over again. When we talked about how many one-to-one functions, once I picked an output, once I said, oh, this element of S is going to map to that element of T, if the function's one-to-one, I can't pick that same element again, right? So the number of choices that we had as we kind of moved on down the line was decreasing. And here we would say that we're selecting without replacement. Once I pick an element of T that some element maps to, I can't pick it again. So when you're doing multiplication counting principle and you're drawing from the same set, that's one of the questions that you want to answer, or like just be clear on as you approach it. Let's do one more multiplication counting principle. So let's suppose we have a set S with 5 elements. How many subsets are there? Now we already, I think, know the answer to this question, or at least we've mentioned what this should be already, but it was way back near the beginning of the semester. Does anybody remember if I have an element, or if I have a set with n elements, how many subsets it has?
Talking about power sets, right?
Yeah, like how big the power set is. Yep. It's not squared. You're thinking along this.
Isn't it 2 to the power of however many elements
Yeah, 2 to the n, right? So we already said, I think we just stated it as, oh, this is a thing that's true. But if a set A has n elements, then the power set of A, the number of subsets is 2 to the n. We're going to derive that fact for ourselves. That's what we're doing in this example. So we have a set S with 5 elements. So let's suppose, I'm going to list them. S consists of the elements A1, A2, A3, A4, A5. We're going to define a one-to-one correspondence between bit strings of length 5 and subsets of S. So here's that correspondence. For each subset A of S, you'll say that the ith bit of the corresponding string is 1 if A sub I is in the set A. If A sub I is in the set A, and it's 0 if it's not in the set. So for example, the set A1, A2, A5, that's a subset of S, right? That corresponds to the bit string 11001, where I'm going to let the first bit be the leftmost, but you could define it the other way if you like. What would be the bit string corresponding to that set, the set that just consists of the element A3? Say that again.
Is it going to be 0, 0, 1, 0, 0?
Yeah. Yep. What about the empty set?
All zeros?
Yeah. So it's a pretty straightforward correspondence. Any element like A sub I of S is either in your subset or not in your subset, and that corresponds to that bit either being 1 or 0. So we have a one-to-one correspondence. Because this is a one-to-one correspondence. And as we deduced on the last page, there are 2 to the 5th bit strings of length 5. Then there are 2 to the 5th subsets of S. And of course, more generally, there are 2 to the k subsets of a set with k elements. Questions so far? Okay. All right. So, all right. So we got some practice with the multiplication counting principle. Next, we've got the addition counting principle, and this is a really kind of particular set of circumstances where this works. So we have a set of pairwise disjoint sets. That's really important. What is pairwise disjoint? What does disjoint mean? Like if two sets are disjoint, does anybody know what that means?
You mean they're not connected in any way?
Yeah, it means there's no overlap, like their intersection is empty, right? So pairwise disjoint, we're not saying that just as a whole group that their intersection of all those S1, S2 up to SM, that they don't all overlap together. We're saying if you pick any two, there's no overlapping, right? The Venn diagram of those sets would be a bunch of isolated little circles where none of them overlap with each other. So if I have pairwise disjoint sets and like SI contains n sub I elements, then the number of elements that can be selected from S1 or S2 or all the way up to them, all the way up to S sub m, is the sum of their sizes. In other words, the size of the union of them all is just, you add up all the sizes of the individual sets. That's super important here to understand that that's only true if they're pairwise disjoint, if none of them overlap. If we have any overlapping, things get a little bit more complicated. And we'll talk about that in the next section. We're going to do an example where we'll get to use that theorem. So we're going to figure out how many integers there are between 0 and 1,000 that have one or more sixes as digits. 0 and 1,000 inclusive. So we're going to include 1,000, although I don't know that that detail is especially important, since if we're counting how many of them have one or more sixes, obviously 1,000 is not one of those. So you know, think about the integers from 0 to 1,000. Like the integers we want to count are like 6, 216, any of the 600s, 161. So we're just figuring out how many integers have at least 1 6 in them. So let's go about it kind of backwards, in that I think it'll be easier to count how many have no sixes, and then we can just subtract that from our total number of integers. So from 0 to 1,000 inclusive, there are 1,001 integers, and we'll figure out how many have no sixes, and then we'll just subtract. So let's let S equal the set of integers between 0 and 1,000 with no sixes. And now what we're going to do is break S down into some disjoint subsets. So we'll let S1 be the subset of S, all right, that has exactly one digit. So in other words, S is the set of one-digit integers that don't have any sixes. So let's see if we understand this. How big is the set S1?
That's right.
9?
9. Why not 10?
Oh, yeah, zeros included is 10.
Well, no. You're right. It is 9, but I'm asking why is it not 10, right? Somebody suggested it was 10.
Well, for
Yeah.
6 is
You go through 6.
Yeah, we got to take the 6 out. Yeah. All right. So now we're going to define S2, S3, and S4 similarly. So S2 is a set of all 2-digit integers with no 6s. So S will have numbers that can have exactly 2 digits. And I'm wording it like this because note that S1 and S2 are disjoint, right? If all the integers in S2 have exactly 2 digits, and that doesn't include any of those 1-digit integers. So how big should that set be? And in fact, say that again?
81?
Nope.
79?
Nope. If you're trying to do a brute force counting, like that's going to be harder. So these integers have 2 digits, right? And if they're 2-digit integers, we don't begin. Sorry, say that again.
Is it 78? Because we have 66 with 2 6s in there.
But you're not counting anything in the 60 range.
No, but so I'm going to suggest a different way to think about this. We know that an integer that we're including has 2 digits, right? And if we're talking about 2-digit integers, we're going to exclude the possibility of it having a leading 0, right? So it's a proper kind of 2-digit integer. What are the choices? Like, how many options do I have for that first digit? What could that first digit be?
No, elevator 9. No, it could be 1 through 9. You're talking about
It can't be 0. What else can it not be?
6.
So how many choices for the first digit? 8. Great. And then how many choices for the second digit?
also the 88.
No.
No.
89.
I'm just saying like the number in total.
It's not 88 or 89. But there are 9 choices for that. The second digit can be 0, right? But it can't be 6. So what we're doing here now, the way we're counting up the size of S, whoops, this is S2, not S1. The way we're counting up the size of S2 is we're using the multiplication counting principle. So it's not 89, it's 8 times 9. Or 72. For each of the 8 ways I could pick that first digit, there are 9 ways I can pick the second digit. So let's keep going. If we think about the integers with exactly 3 digits, meaning no leading zeros, and then these integers have no 6s at all. How many options for that first digit?
8.
8. Second digit?
8.
Why 8?
I thought it was, I thought
Maybe
it was
9.
Oh, it could be 0 now.
Now it can be 0, yeah. So second digit is 9, third digit? 9. And if we multiply these, we get 648.
Hang on, how is the second digit 9? I thought we were still excluding 6s.
Yeah, but
yeah.
but we can include 0 once we get to the, yeah,
Gotcha, we can't put 0 in there.
right. And now this one's actually going to be easy, the S4. Not because, in fact, this pattern doesn't continue. We're only looking for integers up to 1,000. So there's only one integer to consider, and it doesn't have any 6s. So exactly 4 digits. And the size of that set is 1. So these are pairwise disjoint, right? S1, S2, S3, and S4. there's no overlapping. Your integer either has 1 digit or 2 digits or 3 digits or 4 digits. It can't have, there's no overlapping there, which means that the size of our set S up here, the number of integers between 0 and 1,000 that have no sixes, is just the sum of these sets here.
$730.
730. So now that is the number of integers with no sixes. We were asked to figure out how many of the integers are there that have one or more sixes, that have at least one six. So what we need to realize is that we found, like, S is the complement of the set that we're interested in, right? You either have no sixes or you have one or more sixes.
749.
Are you sure?
271.
So 9 plus 72, 648, plus 1, I got 730. Yeah, because S4 has one integer, yep. So then, let me, we had 1001 minus 730, and that, you said 271, Eric? Was that Eric? Okay. 271 integers with one or more sixes as digits. I like this problem because, first of all, we got to use the addition principle, and then involved in that, we had to use the multiplication counting principle. We had to think about how to figure out what those integers were included. We had to think about it in a different way. I mean, the first thing that usually comes to people's minds is they're like, okay, how many in the 600s, how many in the, and you start kind of brute force trying to count them, and boy, you find out pretty quickly like that's a big problem. But the problem becomes a lot easier if we kind of split it up into these smaller problems and use that multiplication counting principle. And then the nice one nice sort of final feature here is that we went about it by finding the size of the complement first and kind of went through the back door to get to the figure that we were interested in, which is not uncommon for that to be an easier way to solve a problem. Let's do another. So here in this next example, we've got a shelf that contains 15 books on computer science, 12 on mathematics, and 10 about chemistry. And we want to select 2 books, each from a different subject. Okay. So, and there are 15 different computer science books, 12 different mathematics books, right? They just sort of categorize them. We want to walk away with 2. We want to walk away with 2 books. Yeah.
Sorry to butt in. We are confused in Williston as to why the answer is not 271.
Why it's not 270?
Oh, why it's not 270, sorry.
So the integers between 0 and 1,000 inclusive, that means there's 1,001 integers there. So I took 1,001 and then subtracted 730. Is that okay?
Yeah. Sorry.
Okay, so in example 3.5, we want to walk away with 2 books, but they have to be on different subjects. So the first thing I might think about doing is categorize, what are the different topics I could walk away with. I could walk away with a computer science and a math book. I could walk away with a computer science and a chemistry book. And I could walk away with a chemistry book and a math book. I think those are the only ways we could pick 2 subjects from the 3. And these are pairwise disjoint. And what I mean when I say pairwise disjoint here is that is not that they couldn't walk away with the same computer science book if I looked at the computer science and math versus computer science and chemistry, but what I'm saying is the pair of books are not going to be the same, right? I can't walk away with a computer science and a math book and have those be the same books that I get if I walked away with a computer science book and a chemistry book, right? They preclude each other. So these are pairwise disjoint. So if I could figure out how many ways I can select one of each of these 2 topics, right, down the line, then I get to just add them up, right? That addition principle says if they're pairwise disjoint, I can find the size of the union just by adding the size of the subsets. So how many ways could I pick one computer science book and one math book? And how do we get it? I guess that's really what I'm after, is how do we get it?
Is it 15 times 12?
15 times 12, 15 because there are 15 computer science books and 12 because there are 12 math books. That's exactly right. And 15 times 12 is 180. How many ways to pick a computer science book and a chemistry book? 15 times 10, yeah, which gives us 150. And then what about a chemistry book and a math book? Yeah, right, because it's 10 times 12. And now all we need to do is add these up. So we get 450. Questions on that example? Okay. All right. When we use that addition counting principle, the one that we used on this one in the last example, where we're kind of breaking it down into these pairwise disjoint or mutually exclusive outcomes, what we're basically doing is partitioning the set that we're interested in. Everything that we're interested in is accounted for, and there's no overlapping between those outcomes. Now, that addition counting principle is really nice, but it requires, forces us to make sure that we have disjoint sets, and that's not always the case. If our sets are not disjoint, we can still find the size of their union. We just have to be a little bit careful. So let's suppose now I've got a couple sets, and maybe they are allowed to overlap. And if I want to figure out how big the union is, I'm going to take all the elements in S. So I've counted those up, right? And then I'm going to add however many elements are in T. I'm counting those up. But as we can see here with the Venn diagram, this bit right here, we counted those twice, right? The elements in the intersection, these were double counted, which is not advisable, right? Definitely gives us an inaccurate answer. But that's easy to fix. If I know my two sets can overlap, then when I want to find the size of the union, I'm going to take the size of S, add the size of T. I double counted the intersection, so I'm just going to subtract it off, and that's what we have here in theorem 3.3. That addition counting principle in the last section is just a special case of this rule right here. If they're pairwise disjoint, then the size of the intersection is 0. So it just kind of reduces to that special case. Let's do an example. Venn diagrams can be a nice way to organize the information you have in a counting problem where we need to use this addition rule. So in example 3.6, the setup is we have 100 students total, 60 of them are taking math, 75 are taking history, 45 of them are taking both. Let's draw the Venn diagram. So all the students taking math. Here are all the students taking history. Now I want to sort of put in some numbers. I want to make sure all 100 students are accounted for. When you're filling in values in a Venn diagram, always start on the inside and work your way out. The one thing I know for sure is that 45 students are taking both, so there's 45 in this overlap. Now they tell us that 60 students take mathematics, but that includes the students who are taking both, right? Those students are taking mathematics. So what number goes over here in like the math crescent shape? Say that louder. 15, yep. Because that'll bring us to a total of 60. How many in the history like crescent shape? Mm-hmm. Yep. Now, if we add all of those up, we get 90. So not everyone's accounted for yet. Because there are 100 students total. Where are those 10 students? What do we know about them?
And either taking math or history, I think they're outside.
Yeah, yep, so those 10 students go out here. They're not taking math or history. So when we answer question A, how many take math or history, we want the size of M union H, right? We want the whole, like, I guess the MasterCard logo there. So this will just be, there's a couple of different ways we can think about it. The theorem 3.3 up here says this should be the size of M plus the size of H minus the intersection. And this will work. This will work just fine. 60 plus 75 minus 45, and that gives us 90. Alternatively, if you go through the trouble of making a Venn diagram, all you have to do is identify the region that you're interested in, right? Like, how many are taking math or history? That means I want to include, I want this region. So just add the numbers that are included in that region that you're shading. And that adds up to 90. So that's part A. And then how many are taking neither math nor history? That's, let's see, M complement intersect H complement or the complement of the union. And that's 10. We kind of answered both of those questions as we were kind of filling it out, just making some observations. But if we wanted to kind of indicate with some like set theoretic notation, then there we are. Want to do another? Yeah. All right, how many positive integers less than 1001 are divisible by 3 or 5? So less than 1001, that means we're including up to 1000. How many of them are divisible by 3 or 5? So right off, here's the word that catches my eye first, is the word or. If I see or, I know that's a union. So I'm going to let A be the set of integers that are divisible by 3. And let's see if we can't figure out a clever way to count up the size of A. The integers divisible by 3 is precisely every third integer, right? So I go from 1, 2, 3, 4, 5, 6, and I just want to know how many up there up to 1,000 are divisible by 3. If it's every third integer, I'm just going to take 1,000 and divide it by 3, right? That'll tell me how many of them there are. Now the trouble here is that I get a decimal. And when I'm counting up the integers, I know there's only going to be a whole number of integers. So when we do that division, we get 333.33333. How many integers are divisible by 3? Like, what is the size of A? Because it's not 0.3333. Like, we're not including decimals.
Just knock the decimal off.
Yeah, we will just knock the decimal off. And it's 333 and not 334 because that 0.33 tells me how close we were to getting to the next integer that's divisible by 3. So I'm going to just apply the floor function here, which just rounds it down, right? Knocks off the decimal part. This is 333. So I'll let B be the integers that are divisible by 5. We'll find that the same way. Every fifth integer is divisible by 5, so 1,000 divided by 5. We don't need the floor function there, but I'm just in the habit. Yeah.
I've just never seen the floor function written out before, so those brackets denote that you're rounding down, not rounding up.
Yeah, the floor function. So there's just it's only bracketed on the bottom.
Okay.
And not on
So
top.
the ceiling would be.
Yes.
Ceiling would be on top.
Yes.
Okay.
Yep.
Sweet. Thank you. Just never seen that before.
Yeah. So there's our, so there's 200 divisible by 5. Now if I just add those up, I've double counted some integers. In particular, I've double counted, 15? Right, that's divisible by 3 and 5. I want to remove those. So the integers that are divisible by both 3 and 5 are precisely the integers that are divisible by 15. So the size of A intersect B, because I'm going to take 1,000 divided by 15, apply the floor function. And we get 66. Now we're just going to put this together. The integers, the number of integers divisible by 3 or 5, that's the size of A union B, which you know is the size of A, plus the size of B, and then subtract off their intersection so we don't double count those integers divisible by 15. So 533 minus 66 is 467. Almost half of the integers, less than 1,001, are divisible by either 3 or 5. That's not super surprising. I mean, you take the smaller your divisor is, the more of them there are, right? And I took a pair of pretty small divisors. Okay. Questions about that example? Okay, so this one's pretty fun. We want to know how many ways are there to arrange the integers from 0 through 9 so that the first digit is greater than 1 and the last digit is less than 7. We're talking about arrangements of this set of integers, so we're not repeating them, right? We're saying I have this fixed set. I've got 1 0 to use, I've got 1 1 to use, I've got 1 2, and we're just thinking about arranging them, like taking them, scrambling them up, and putting them down again. There's an arrangement. And we want to know how many ways we can do that so that the first digit is greater than 1 and the last digit is less than 7. I think this one might be easier to do kind of using the complement again. So I'm going to say our universal set will just be all arrangements where I have no restrictions on it at all. And sometimes when I'm going about a counting problem, I might start there, is say, you know, there's sort of two directions you can go in. One is, what if there are no restrictions? So I'd get like a much bigger value, and then you could start about thinking about adding restrictions. And then the other direction you can go in is, what if I put on lots and lots more restrictions, which so my set gets smaller. Our universal set here is just going to be all arrangements with no restrictions. So how big is the universal set? Like, so I've got 10 digits, right, from 0 to 9. How many ways can I pick the first one?
10.
Yep. So let's say I picked it. How many ways to pick the next one? It's not the same because they said how many ways are there to arrange these integers? So we're talking about arrangements. We've got like a single one of these digits. So once I use it, I can't use it again.
10 minus 1 is 9.
Yeah. Mm-hmm. Right, and then 8, 7. Right, once I've used a digit, I can't use it again. Times 2 times 1. We usually call this 10 factorial, which is large. So I'm going to define a couple of sets. I'm going to let A be the set of arrangements where the first digit is 0 or 1. Notice that that is exactly the complement of what I'm looking for that restriction. Right, because they talk about the first digit being greater than 1, right? So I'm just taking the complement of that. And we'll let B be the set of arrangements where the last digit, let's see, they ask about the last digit being less than 7, so I'll let B be the arrangements where the last digit is 7, 8, or 9. That's the complement of what we're looking for. And with this in mind, what we want are all the arrangements that are not in A or that are not included in A and not included in B, right? Because we want the number of arrangements where the first digit is greater than 1 and the last digit, where both of those requirements are met. So that means what we're looking for, the arrangements we want cannot be included in A and they cannot be included in B. So we want the size of A complement intersect B complement, or the size of the complement of the union. So let's see if we can't figure out how big A and B are. We know how many, like the universal set, right? The arrangements where there are no restrictions is just 10 factorial. With A, we're adding one restriction. We're saying we need that first digit to be 0 or 1. So that means I've only got 2 choices for that first digit. There are no other restrictions, though. So the rest of the 9 digits can be anything, and that's going to give me 9 factorial, right, for the rest of those. To figure out the size of B, we want the arrangements where the last digit is 7, 8, or 9. We are in a habit of always thinking about, let's pick the first digit first, because naturally, why wouldn't we do that? But why don't we go ahead and pick the last digit first, because that's where our restriction is. Take care of the restrictions first. How many choices do we have for that last digit? Yep. And then after that, the rest of the 9 digits can be anything. So 9 factorial. Now, what about arrangements that are in their intersection, where both of those restrictions are met? How many choices for the first digit?
2.
2. So pick the first digit first. Now let's pick the last digit. There are 3 choices there. And that leaves us with 8 more digits to place with no restrictions, so 8 factorial. And we can use this to find the size of A union B. So that's 2 times 9 factorial plus 3 times 9 factorial minus 2 times 3 times 8 factorial. And you could find each of those individually. Your calculator can do factorials. So if you hit the math button, and then there's a PRB or PROB menu, that's probability. So if you arrow over to that, option 4 is the factorial. So I've got 2 times 9 factorial plus 3 times 9 factorial minus 2 times 3 times 8 factorial. I get 1,572,480. So now we're almost done. We want the complement of this, right? We outlined that at the get-go. So the size of the complement of A union B. I'm just going to take the size of the universal set, which is 10 factorial, and subtract 1,572,480. $2,056,320. Questions on that one? Okay. We've been looking at that addition counting rule that involves 2 sets. You can generalize it to more sets. Here's how it looks if you have 3 sets, and it looks pretty familiar at first, right? It says we're gonna, if I want the size of A union B union C, right? I'm gonna just first add all 3 of those, but I've double counted a bunch of stuff. In fact, let's see what we've double counted. So let's see, here's A, B, C. So let's see, I grab A, then I grab B. I'm doing this in different colors so we can see the overlap that we're double counting. So right now, I've double counted A intersect B, right? And when I shade C, I've double counted a bunch of stuff. Right? There's a whole slew of things in the middle that have been double counted. So what we want to do is subtract off all those intersections. subtract A intersect B, so I don't double count that, subtract A intersect C, so I don't double count that, and subtract B intersect C, so I don't double count that. The problem that we run into that we can account for is that once I've subtracted all three of those intersections, I will have subtracted off where they all overlap here in the middle. I will have counted it 3 times and then subtracted it 3 times. I want to count it once, right? So that's why we add the intersection of all 3 at the end. One more example to do where we can make a Venn diagram with 3 sets. And again, if you're going through the trouble of making a Venn diagram to help you count something, you don't necessarily need to use a formula to help you do the counting. Really kind of just depends on how the information is given to you and what's most convenient. Again, we've got 100 students surveyed, and we found they're taking different courses. 50 of them are taking chemistry, 50 take math, 42 take physics, and then we have different numbers that take both, like chemistry and physics and math, and so on. And then with five lucky students are taking all 3. We want to answer some questions, and our work will be much easier if we just take a few minutes and make a Venn diagram to help us organize. So we have chemistry, math, and physics. When you're filling in numbers for a Venn diagram, always start on the inside and work your way out. So the one number I'm 100% sure about where it goes is the 5 students that are taking all 3. That means I'm going to put a 5 right in dead center. Now I'm going to move out to the other intersections. So they told us that 15 take chemistry and physics. So chemistry and physics, that's this part. And I've already counted 5 of those students. So that leaves 10 that are taking chemistry and physics but not math. 20 are taking physics and math. So physics and math. That's that intersection there. And again, I've already counted 5 of them, so that leaves 15 for taking math and physics but not chemistry. And then 25 take math and chemistry. So that's that intersection. We've already counted 5 of them, and that leaves 20 that take chemistry and math but not physics. Now we can move out one more layer. So this part here where I've got the star, the chemistry, those are students taking chemistry but not math or physics. So 50 students take chemistry. That includes the 35 that are there, which leaves us 15 students that take in that region. Then how about the math but no chemistry or physics? So we have 53 taking math, and I'm just going to subtract the 25 and 15 that are already in the math circle. So 53 minus 25 and 15 is 40, so that's 13. And then 42 take physics, but that includes the 10, 15, and 5 that are already in the physics circle. So 42 minus, 12, yeah. And then if you add them all up, all these numbers up, they add up to 90, so that means that there are 10 students on the outside. Part A says how many students are taking at least one of these. We want to know how big is their union. And I'm not going to write out all the addition, but we're just going to add all these numbers that are inside any of the circles. So the 15, 20, 13, 10, 5, 15, and 12, when you add those up, that's the 90, yep. And then for B, we just want the complement, and we've already found that. That's the 10. Right, that's the students that are outside all the circles. And then how many take physics or chem, but not mathematics? So if we were to kind of denote that using some set notation, we want them to be in the physics or chemistry. So the union of physics and chemistry, but not math. So I'm going to intersect that with math complement. That's just a little bit of notation. We can identify what we are talking about in the Venn diagram. Physics or chemistry, but not math. I think that's this part here. Oh no, that's not chemistry. That's physics or chemistry, but not, oh, I think it's just the 10, right? Physics? Oh, physics or chemistry, not and. Physics or chemistry, but not math. So we're going to add those three. That gives us 37. We don't quite have enough time to get to the last example, so we'll do that one on Wednesday and then talk about combinations and permutations. If you have more questions as you're working on the test, feel free to reach out via text or email. Or you could use Canvas messages. That works pretty well too.
Canvas does a messaging system?
Yeah, there's Canvas Mail. Like if you go into Canvas, there's an inbox here. So that's where you'll find your messages. And then also, I think if you go to Home, so I'm looking at the instructor version, but I think like there might be either on the left or on the right a thing that says like message my instructor. Yeah. And it works pretty well. Thanks, everybody.